Hello everyone, this is Dr. Young, and in this video we are going to start our discussion about gases. So this is just an introduction to what they are. You might already know a lot of this stuff already, but I just want to make sure we start off on the same page before we start getting into the details. So, what are gases? Again, you may have heard of this before. I apologize if I'm sounding like I'm being patronizing, but here's what they are, right? They're one of the three states of matter: solid, liquid, gas. Now, there are things like plasmas, and there are, supercritical, fluids and everything. We're not going to talk about any of those at this point. This is just normal gases, everyday gases. And they're important, which is why they get their whole own chapter in most books and stuff, right? First of all, most of the universe is gas. We don't normally think about that because we're Earth creatures, so a lot of everything for us is solids and liquids. We just breathe gas, and then we assume that's basically all it is. And we don't normally think about gases, right, unless they're killing us or they're stinky or something like that. We don't normally think about the gases that are around us. But like I said, most of the universe is gas. Most of it is hydrogen and helium gas. It's not a bunch of solids. Most everything is in this phase. Other examples, right? Like I was just saying, we think about gases in terms of the air that we breathe, which is more, a little less than all of the atmosphere. The atmosphere has lots of different levels, lots of different compositions. There's things like ozone, which is different than the nitrogen and the oxygen that we're breathing. Hopefully you're not breathing a lot of ozone because that would really damage your lungs. And then there's also things like greenhouse gases, right? We hear that term all the time in the news with global warming, climate change, greenhouse gases. So these would be things like carbon dioxide, of course, but also things like methane and those refrigerants, those CFCs, those chlorofluorocarbons, all kinds of refrigerants. Refrigerators, speaking of which, refrigerators use gases, right? And part of the compression and decompression cycle that they go through to get cold. Most air conditioners, not all, but most air conditioners also use gases. Helium balloons, that's super fun, right? You got bouncy balloons, kids love them. They are kind of cool still. You can breathe them in, talk funny. That's a helium balloon. And it makes your voice talk funny, right? Because it's got a different density than the density that we're used to breathing, which is the air blend. So when you breathe a helium balloon, you're breathing a blend that's a different density, and so your throat vibrates at a different pitch. Fun fact, if you breathe in argon, which I don't recommend you do for a couple of reasons, but if you breathe in argon, it actually makes your voice lower because it has a higher density than the air you breathe. If you ever get your hands on an argon balloon, it's super fun. If you do it though, maybe lay down on the ground because argon is heavier than air and you can suffocate yourself. So don't do that. Bubbles in baking. I just made some brownie things with my kids. We make bread, right? It's the pandemic. Everyone's making bread. But the bubbles in your baking goods, for example, those are all gases, right? Decompositions of baking soda or something like that, or the bubbles produced by yeast, the carbon dioxide bubbles produced by yeast. And then there's toxic gases, the very unfortunate war gases, or just toxic gases that you don't want to breathe in, like, for example, carbon monoxide from the tailpipe, all kinds of terrible things like phosgene gases, stuff like that. And then there's the gases that we use as fuels, right? Natural gas is a big thing right now. A lot of talk about fracking and getting natural gas out of the ground. Natural gas is mostly methane, which is CH4, but there's things like propane. A lot of people have propane piped into their house so they can have gas stoves or gas water heaters or something like that. My point is, gases are a lot of places, so it's worth knowing something about gases. How do they behave? What happens when you change the pressure or the temperature or the volume of the gas? Those sorts of things. How much gas do you produce in a reaction? So we're going to talk about all of those things. Not in this video. We're just going to introduce gases in this video. But we're going to talk about all those things through this series, through this playlist of videos. So the first thing I want to talk about with gases, again, this is just an introduction, is how they are similar to or different from the other phases, namely solids and liquids. So I want to talk to you about the vibrational speeds, the particles that make up the gas versus that make up the solid. What's their vibrational speed like? How much do they jiggle? What are the relative densities like? Do they fill the shape of their container? Does their volume depend on the container? Are they compressible? Those sorts of questions. So we're going to switch over to a simulation, and I want to talk about that simulation. Okay, so what I have here is a simulation from PhET. It's this program with University of Colorado. It's pretty cool, but I just wanted to use it to show you some of the different phases in case you haven't seen anything like this before. So what I'm starting with right now is oxygen. You can change it to argon and neon and water. And I'll post a link to this so that you can play with this on your own too. But I'm going to start with oxygen, right? Good old O2, which is why you have these two little red spheres bonded together. And we're starting off at 27 Kelvin, which is very cold, right? Negative 246 degrees Celsius. That's super, super cold. And right now, oxygen here is just in a big old square. They're kind of wiggling a little bit because they have some energy, right? This is not absolute zero. It's not 0 Kelvin. So they have some energy, so they're vibrating just a little bit. This is oxygen in its solid phase, right? We talked about those properties that we're going to take a look at. It's got a very distinct property. Its volume, right, is not being determined by the size of this container. I've got a big old container, but I've just got a little square of this solid O2. Particles aren't really moving all that much. Looks pretty dense. We'll compare and contrast it to other phases here in a sec. But what I want you to pay attention to is what happens when I start to heat it up some, right? So I'm going to add some heat. I love this little thing. Ice for cold, fire for heat. And you can see my temperature going up for Kelvin here. Now, you may notice a difference here. It's no longer kind of in a nice, unique, defined shape. It's kind of moving around. Some of these oxygen molecules are sliding past one another. It's much looser. This would be a representation of what a liquid is like. The O2 molecules are still attracted to each other, but not as much. And you can see even here's a couple flying away a little bit. But their shape is changing, right? And if I had more of these, I wonder what happens if I do this. Well, I can add more apparently. I'm going to add a whole bunch more of these. I'm raising the temperature by accident. If I add more of these, in theory, what would happen is that these O2 molecules would start to, come on, cool down, guys. Come on back. There we go. These O2 molecules would take the shape of the container, right? As you know, for things like water, water's going to take the shape of whatever container it's in. If you have a square glass, it's going to be a square shape. If you have a round glass, it's going to be a roundish shape. If you have a tall, skinny one, it's going to be a tall, skinny shape. If you have a short, wide one, it's going to be a short, wide shape. But if I keep on heating this up, we're going to get to the state of matter, the phase that we are really interested in, which is gases. So I'm just going to keep on heating this up. And now you notice that those oxygen molecules are no longer really sticking to each other very well. They're flying around, they're kind of doing their own thing, they're bouncing off the walls, they're bouncing off each other. Some are moving fast, some are moving slow, but this would be O2 in its gas phase, right? In our gas phase. So here we're still pretty cold. We're still 61 degrees below freezing. Let's just get to 0. But these oxygen molecules are now in the gas phase, right? I didn't break any bonds in terms of like the oxygens bonded to each other, but I did ruin their attractive forces, which is something we'll talk about later. So here I have my gas, right? Notice that it takes up the entire volume of this container here. It's not very dense, right? If I pause this at any moment, there's lots of gaps between O2 molecules, right? There's lots of gaps. There's some places where there are smaller gaps, but there's lots of gaps, so it's not a very dense phase. One other thing I wanted to show you here is it actually is kind of monitoring the pressure for us. It's saying it's about 1920 atmospheres or so, right? Which is a way to measure pressure, which we'll talk a little bit about in a second. But what's happening with the pressure is that the pressure is basically comes from the collisions of our O2 molecules with the sides of the container. So every time an O2 molecule hits the side of the container, the pressure goes up because of force. The force on the side of the container increases. And at any given moment when there's not a lot of O2 molecules hitting the side of the container, then the force kind of goes down. That's why it's not really constant here for this number of O2 molecules. It's bobbing up and down because at a certain time, only so many air molecules are actually hitting the sides, is the idea. And we can change the pressure. We'll talk way more about this in a future video. But if I increase the temperature, notice that the pressure should start to go up because I have my molecules moving faster, so they're more energetic and they're going to have more collisions. So if I keep on heating this up, right, I was at 20, now I'm more at like 26. Same thing if I decrease the volume so that now, oh, I've got more little guys in an area here. So now I get more collisions with the side. The pressure went way up. Now we're at like 80 something. And pressure is a super important property of gases, which is what I want to talk about next. But first, let's kind of go back and finish that diagram that we had. So you've checked out that simulation. We're back at this diagram here, this chart. So like I mentioned, right, as far as the particle speed movement, solids definitely just jiggled a little bit, right? They didn't move much. They just kind of stayed in place and they jiggled a little bit. So solids would definitely be the slowest. Whoop. Let's see if I can write on this. So slowest. Gases were definitely the fastest, right? They were flying around all over the place. Liquids were somewhere in between. They're the medium one. Gases flew all over the place. Solids pretty much stayed in one place, but jiggled a little bit because they had some energy, right? Even if you look at your table right now or your phone or your computer, technically on an atomic level, all of those particles, those atoms or molecules are vibrating slightly because we're not at absolute zero. So they have some energy. Density, we talked about the density. There's lots of space in between gas molecules, but there was not much space in between solids when they were, between the molecules when they were solids. So solids are the most dense usually, though not often. I'll put often the most dense. And then usually gases are always the least dense. So always the least dense. There are things where the liquid and solid densities are switched. So water is a great example of where the solid is less dense than the liquid is. And there's lots of elements. There's like germanium and things like that. There's a lot of alcohols like T-butanol, tertiary butanol, that are actually have less dense solids than they do liquids, which is why ice floats on water instead of sinks in water. And we'll talk more about that later also. Does the shape of the substance depend on the shape of the container? For solids, right, that answer is no. If you have something solid like, say, I always use the example of like my wedding ring because I have it on me, but like, your car keys or your pencil or whatever, that if you put it doesn't matter what container you put your pencil in, it's always pencil shaped. It doesn't matter what the container is. So no, the shape does not depend on the container. Liquids, however, right, like I mentioned in that simulation, liquids do change their shape depending on the container they're in, right? So you pour it in a square glass versus a round glass and it's going to change its shape. So yes, liquids do, and absolutely gases do, right? Because gases just fill the whole container they're in. So if you have a round container like a balloon or a square container like, I don't know, just like a room, the gas is going to take that shape. Now, does the volume depend on the container? Definitely not for solids, right? It's not like the volume of your pencil changes depending on which size room you take it to. The volume also of liquids does not change, right? If you have 1 teaspoon of water, it's not like if you put it in a bigger glass that it's suddenly more than a teaspoon of water, right? It's the same amount, right? If you try to pour a 1 gallon thing of milk into a 1 cup measuring cup, it's gonna overflow. But if you pour a 1 cup thing of water into a gallon container, it's not going to overflow, right? The volume doesn't change with the container. Gases, though, it does change because the gas is just going to fill the whole container it's in, right? It's just going to expand or contract to fill the thing it's in. The example I always use in my in-person classes is, do I want to do this? Yeah, why not? Well, I'll use this example. Like the stink bomb. Like if you have a little stink bomb, I don't know if anyone's ever used these, right? These little like vials of super stinky stuff. At that point, the gas is just in that little tiny vial that you have, right? It's in a small vial. It takes up a small volume. But as soon as you smash it on the ground, right, it's going to start expanding and it's going to fill the entire room that you're in, right? It's going to make the whole room stink. It's going to be awful. But that gas is then going to occupy that whole room that you're in. So its volume expands and takes up the volume of the whole room you're in. And then if you open the door to that room and then some windows and stuff, then it's going to leave the room and then it's going to expand basically, all of the area of the earth that it can get to. It's just diffuse away basically. But its volume does depend on the size of the container that it's in. Which also leads us to this last one. Is it compressible? Generally speaking, solids are not compressible, right? You can't take your pencil or a wedding ring or your table and squeeze on it and change the volume much, right? If you can change the volume of it, it's because it's got air bubbles in it and it's not actually fully solid throughout the thing. Liquids, generally, I'm going to say not really. And I'm saying not really because y'all are going to take chemistry at some point and realized that gases are slightly compressed, or sorry, not gases, liquids are slightly compressible, and it depends on the liquid, but not really. So I'm just going to put a no here, but parenthetically, not really. But gases absolutely are compressible. You can compress them like crazy. It's totally fine. Right, I showed you in that previous simulation. We just compressed the gas. We're able to make it smaller. It's how car engines work, right? You got compressions in the pistons of the gases, and then the expansion of those gases to move pistons and everything. You absolutely can compress it. You can imagine like a syringe, an empty syringe filled with just gas, and you cap off the end. You can still pump that syringe just fine because you can compress that gas. So that's just a basic overview of some different properties of gases. Again, I'm going to want you to focus on kind of these things, right, for our discussion of gases. But it's good to have in the back of your mind how they're different from solids and from liquids. So we also need to say a couple things about pressure. Pressure is a particularly important property for gases, not so much for solids and liquids who don't really feel the effects of pressure in the same way that gases do. It's really important for gases. And this comes into play for a lot of practical applications too. I scuba dive some. I don't know if anyone else out there scuba dives, but really important for scuba divers because of the different pressures that you're putting your body under. When you dive down, the pressure of the air that you breathe goes way up. And that has all kinds of consequences. You need to worry about things like decompression sickness, which is also called the bends. You have to worry about things like nitrogen toxicity, and there's other issues you need to worry about, but it's all because of those changing pressures in the gases. Airplanes are things that fly. Things that fly are because of differences in air pressures, right? So airplanes fly because the air pressure below the wing is higher than the air pressure above the wing, so you can keep a plane afloat, right? So without the idea of pressures of these gases, we wouldn't be flying planes anywhere. And then you may have seen pressure effects from when you like drive up a mountain, or I guess airplanes too, but your ears popping, right? That's where you definitely feel the pressure, just the differences between the air pressure in your sinuses and in your inner ears compared to outside, right? You can feel the different effects there. Or you may have seen like a potato chip bag or something puff up if you drive up into the mountains from someplace low. The air pressure decreases outside of the bag and stays the same inside the bag, so it puffs up to kind of try to equalize that. But we see there's lots of instances, and we'll see some more. We'll talk a lot more about pressure in later videos. But what pressure is for gases, right, like I mentioned in that little simulation, is that it comes from the collision of the gas particles against the container. So all of the force from those collisions against the container, that's what makes pressure, right? So the more particles you have, or the more forceful the collisions, the pressure goes up. And so the more you hit the container, the higher your pressure is. And we're not going to get crazy into the physics part of this, but the equation here is just that pressure equals the force divided by the area that force is applied to. So that's P equals F divided by A, where A is area, F is force, and P is pressure. So like you feel pressure, just to give you a sense of the relationship between force and area, right? Like if I push you with all of my force with my hand, I might knock you over, I might not, but you're gonna feel all of the force that I try to give you, right? If I push you with the palm of my hand, but it's not gonna hurt real bad. But if I poked you with the tip of my thumb with all the force I have, that's gonna hurt a lot more, even though the force is the same because I'm the same person. I'm pushing as hard as I can either way. The force is the same, but the area is really different, right? If you divide that force over a smaller number, you're going to have a higher pressure, right? So the pressure, you feel more pressure when I poke you with my thumb than when I push you with the palm of my hand. And it's just an issue of area. So there's this relationship between force and area and the pressure that is felt. And then the units of pressure, we'll talk a lot more about all of this in future videos, but it's atmospheres, torrs, millimeters of mercury, millibars, PSI. There's some others, but there's lots of different ways that you can measure pressure. So in the next video, we're going to talk more about the kinetic theory of gases, a little bit more about the assumptions that we make about gases, how gases behave, and the relationships with like temperature and kinetic energy, stuff like that. To help inform the ideal gas law. And we'll talk a lot about the ideal gas law in future videos too. So good luck studying. Watch the next video. Take care.